My name's Daniel Reynolds. I'm a professor at Southern Methodist University, and David Gardner is up here in the front, and he'll also be presenting in our session today. We're going to break it apart into about 30 minutes of the kind of lecture-y portion. That's going to be me, followed by David for the next 40 minutes or so on hands-on. And the hands-on are going to be interactive kinds of hands-on, where he's going to stop and have you guys answer questions. So be sure you follow those instructions to log into Theta GPU and all that stuff to kind of reserve your node. Maybe don't do it yet, but wait about 10 minutes so you'll have it for the duration of the hands-on. So I'm going to talk about time integration, and I'm going to talk about it kind of in general. I'll give a little bit specifically about sundials, but I'll also talk about ATPESC and Trilinos and how they do time integration as well at a high level. And then, of course, the hands-on exercises will be done using sundials. So often when I've lectured at ATPESC, the audience comes from a wide variety of disciplines. And so there's math, there's engineering, there's biology, all kinds of stuff. So I apologize if I'm going to be a little introductory in some of the lecture material, but I think it's going to match with some of you a little better than others. So time integrators in high-performance computing arise kind of naturally in a number of places. Most models of physical systems are formulated in terms of the rate of change of some variable in terms of other things. So at the simplest level, we can think of Newton's second law, force equals mass times acceleration. And of course, acceleration is just the time derivative of velocity. And so people often use an equation like this if they're doing particle dynamics, and they want to see how particles are moving and how the velocity of those particles is changing as a function of time. You can also have chemistry. So if you have two reactants A and B and they produce a product P, it gives rise to an ODE for how P varies in time. It also affects ODEs for A and B, but I didn't write them up here. In general, time integrators are used to track changes in solutions as time proceeds, allowing studies of the evolution of a model. So it's not that we're not going to focus on steady state here. We're going to focus on how things move and proceed as a function of time. So unlike spatial discretization, which we had this morning, and visualization, time integrators are kind of in the middle of the software stack. So if you consider the following two PDE systems, we can imagine on the left, this is the compressible Navier-Stokes equation, so just gas flow, but it's compressible gas like in air. On the right, we have an incompressible Navier-Stokes. So pretty much the same model, but slightly different use cases for these two systems. If you'll notice in here on the left, every equation has a time derivative term. So all of these, if you move everything except these time derivative terms to the right-hand side, you lump all of your unknowns together, all the density, velocities, and total energies in the whole domain. You can think about it as calling the solution as a function of time just y. And if you move everything to the right-hand side, everything over here becomes this f. And so on the left, we have a system of ordinary differential equations from the time integration perspective, as long as you can somehow discretize all these divergences and gradients and things like that. On the right, we have one equation that has a time derivative term. So there's an evolution equation. But we have a steady state equation, this incompressibility equation for the fluid. And so here, it's not the case that we can write a time derivative of everything on the left and push everything to the right-hand side. But instead, we can have time evolution equations for some components, and then constraint equations for other components. And so this would give rise to what's called the differential algebraic equation, where we encode all of this inside this DAE residual function, capital F. And it's a function of time, the solution, and the time derivative of the solution. And as long as you pose it all appropriately, you could think about evolving this guy as a function of time as well. In kind of standard physical simulations, we often go forward in time. So there's some initial state that we kind of know, or we estimate, or we measure, or we just make up. But then you want to see what things look like further on in the future. You can also go backwards in time if you know the final state of something and you want to see how things might have been before. And the same types of methods we use for evolving things forward in time can be used backward in time with a few minor caveats. OK, so there are space-time solution approaches where you discretize all of space and all of time all at once, and you solve the whole big shebang altogether. That's not the focus of today's talk. But if you are interested in those kinds of things, there are advanced methods called parallel and time integrators and all kinds of things to really focus on that kind of application. And Dave and I can talk to you in hands-on or speed dating or whatever about those things later. But we're going to think about kind of the standard time integration approach, where we aren't going to know the solution at all the continuous values of t, but we're going to know the value, we're going to approximate the solution values at specific instants. So we're going to call those instants Tn, And so if our true solution, we don't know it, but we want to approximate it at different moments tn, we're going to call those y sub n. We're going to say the distance between two successive instants that we want to know about is going to be given by this delta tn. And so instead of trying to know y at all of time, we want to know y at only this set of finite times that we want to get the approximations at. And the standard approach for doing time integration is to do a time marching scheme. So given the state now and some formula is going to be encoded in this capital phi, you want to say, how am I going to evolve from one time, say yn and tn, to the next time yn plus 1? Now, we'll talk more about the structure of these phi functions in a moment, but you can imagine I know things now, maybe I know things in the past, and I do something on my computer to figure out what things should look like in the future, and that's what this capital phi is supposed to encode. Methods you might have seen before, explicit Euler, implicit Euler, you can kind of see this is the phi right here. It's a function of yn, tn, f, etc. Here's the phi for implicit Euler, which is a function of yn and yn plus 1, which we'll talk about more in a second. So there's different types of time integrators, and the three kind of big classes that you might have heard about are going to be explicit methods, implicit methods, and mixed IMEX methods, so implicit, explicit. So if this phi function depends on the solution you're trying to predict, like implicit Euler, I want to know this, but somehow I have to know it on the right-hand side as well, that's going to be called an implicit algorithm. You have to solve for the yn plus 1 that actually works with this equation, and there's challenges that ensue. Otherwise, so you have some nonlinear solve. If you imagine moving all this stuff over to the left, then you could imagine trying to write this as a root finding problem. And so some nonlinear solver or linear solver that's required to solve that system. If the time marching scheme doesn't depend on the new solution, then it's going to be called explicit. And so you could just compute the new solution based on stuff you know already, and that's going to be one of these explicit time marching schemes. An IMEX method is one where some parts of the physical operator you treat implicitly, other parts of the operator you treat explicitly. There's an art form to it, but you try to do that, and we'll talk about kind of why you'd pick an IMEX method in a little bit. There also exist multi-rate methods, which again I'm not going to focus on in this talk, but it's where a lot of our research sits, and you can schedule a time to meet with David or I, and we can talk about all the stuff we're building for multi-rate integrators kind of in a one-on-one session. But in these multi-rate methods, the idea is some parts of the physical operators you'd evolve with a big time step, and other parts you'd evolve with little tiny time steps. Okay, so time integration methods have different approaches for getting high order. And so in general, you're not going to use a time integration library if you're going to do a first order method. You want to use an integration library to do something that's larger scale, more accurate, more adaptive, whatever. So I'm going to focus on the not first step that you might have done already. And so we have different ways of getting high accuracy. So we have two kind of categories in general. One's called a one-step method. The other group is called multi-step methods. And the idea behind a one-step method is, given the state right now, that's all I need to know, plus the physical operators. I'm going to do a lot of work along the way to build up a high accuracy solution for the next time step. And so they build what are called internal stages to do different types of pieces of the approximation to eventually get a high order accurate approximation. And algorithms you might have heard of are Runge-Kutta methods, Rosenbrock methods, etc. Multi-step methods take a different approach. They say, I know the solution now, and maybe I knew it in the past, and further in the past, and even further in the past, and even further in the past. And by knowing this time history of the solution at all this instance, it then predicts one step in the future. And so it's going to use a lot of data to predict what's going on in the future, but because it's retaining a long history of things, it can get high order accuracy in that respect. So another thing you might have heard about, maybe you know a lot about, maybe you don't, but you know it's important, is what's called the linear stability of a time integrator. And so basically what happens is that you can do some analysis to show that round-off errors that always happen on the computer, depending on the time step size you choose, those round-off errors could decay down to 0, or they could grow exponentially. You kind of prefer that the round-off errors don't grow exponentially, and so we do this thing called linear stability, and this analysis of the problem, which is relatively simple, but it helps predict whether the method's going to go unstable or remain stable for a given time step size. If you haven't seen how to do that analysis, but you'd like to, all these slides are on the Slack channel, and so you can download them. And at the very end, I include a little tutorial on how to do linear stability analysis for explicit Euler, implicit Euler, those kinds of things. Okay, so in general, one kind of adjective we really like about certain kinds of methods is whether they're going to be called astable. And an astable method is a method that I don't care what time step size you pick, those round-off errors will not grow exponentially. They're going to remain controlled. That's really only possible with implicit methods. There's this caveat, there's these things called exponential methods, but I'm not, again, if you want to talk about those, you can talk about those with me offline. Those are technically explicit, but they require just as much work as an implicit method, so it's not, there's no free lunch there. If they're not astable, then there's going to be some maximum stable step size you're going to be able to take. And if you take a step size smaller than that, then your round-off errors are probably going to stay controlled. If you take a step size too big, these things explode. And oftentimes, linear stability analysis is a really sharp estimate. I do it in my classes all the time. You do this simple approximation, and then the moment they run with a step size slightly larger than that threshold, everything goes wonkers. Okay, and so non-implicit methods are going to have some kind of upper bound. For PDE type problems, it's often called a CFL condition. You might have heard that acronym before for Courant, Friedrichs, and Levy. But in those scenarios, you can estimate the time step size needs to be proportional to the mesh size or the mesh size squared or something like that. And one of the things I really want to drive home, and I drive it home every time I lecture at ATPESC, is that stability is not at all the same as accuracy. Okay? So often when I work, we do a lot of collaborations with application scientists. And the moment round-off errors don't explode, they think that it's great and they're all done. The pictures seem reasonable, eyeball norm looks okay, but it's not actually the right answer for what you're trying to compute. It's just not the terribly wrong answer. Okay? And so I want you to dissociate the idea of something being stable from something being accurate. Okay? So we're going to focus on accuracy a little bit in detail when we talk about time adaptivity in a few slides. Okay. So how does one choose between an explicit method or an implicit method or IMEX methods or whatever? So some of the positives and negatives you might consider. You all have application problems you're thinking about. Try to think about your application problem and where it kind of fits in this landscape. Explicit methods are really easy to conceptualize and they're very easy to code in general. And they don't require an algebraic solver. They don't require you to solve a root finding problem to be able to do anything. So you aren't dependent on nonlinear solvers, linear solvers, all the other lectures at ATPESC today. However, explicit methods are going to have an upper bound on their stable step sizes. And that upper bound on that stable step size really is going to be a step size that needs to track the absolute fastest thing evolving in your problem. And so if you have some really fast thing that doesn't carry any energy, you still have to take time steps on the order of that fastest possible dynamics. That people often call those parasitic time scales. They're not really contributing anything to what you're trying to solve, but you have to take steps at that really tiny, those tiny steps to track them, or else everything goes crazy. Okay? On the other hand, implicit methods, they might not have a stability limit. So you can take any time step size you'd like, and round-off errors won't explode. Again, it might not be accurate, but round-off errors won't explode. They allow you to step over those parasitic dynamics. You can take a time step size that matches the things you want to track, not what's the largest eigenvalue of the Jacobian of the right-hand side type thing. Okay? Now, they do require algebraic solvers, and so they need a root finding problem, be it linear or nonlinear, depending on the ODE you're trying to integrate. Those algebraic solvers often require that you kind of couple everything on your supercomputer together into one big problem. So obviously, you've been talking about communication and synchronization, all this kind of stuff. So if every CPU and GPU on the whole supercomputer has it all synchronized too frequently, your scalability kind of goes kaput, right? And so this is one of the challenges with implicit methods. Also, obviously, with the moment you have these solvers, you can have some increased code complexity to really get scalability out of this stuff. IMEX methods are a bit of both. You choose which parts you want to treat explicitly and which parts you want to treat implicitly, so that you can take, say, something that's parasitic and isn't really is just going to make you have to take small time steps. If you can treat that implicitly, but the algebraic solver is really straightforward, maybe it's really scalable. That's a really good splitting if it's possible for your application, that sort of thing. Okay, so one of the characteristics of problems that we often think about when trying to decide between an explicit or implicit method is the stiffness of the problem. And so a lot of folks in the time integration community debate the definition of stiffness, but one of the simple ways to think about it is if you did explicit Euler, so the simplest explicit method, and you need to take a step size that was stable, would those time steps be so small that your error would be way more accurate than you ever even care about? Does that make sense? So maybe a stable step size needs to be tiny, but an accurate step size should be much bigger. That's going to be indicative of a stiff application, okay? One that maybe could benefit from all the work associated with an implicit solver, so you can take those time steps that are accurate and still would be stable. The idea of stiffness can depend on Jacobian eigenvalues. So if you have an initial value problem that has an f that was the right-hand side, you differentiate f with respect to y and get a matrix of all these components, and then you take the eigenvalues of that. There's a lot of analysis you could do, but it kind of depends on how big those get. How big of a problem are you solving? How accurate do you want your solution to be? Are you going to do a long-time simulation or a short-time simulation? Those kinds of things. Now, if you have a stiff application, you probably have to use an implicit method or an IMEX method to really be able to get much out of it. And when you do that, now you need some really good, robust implicit solvers, nonlinear solvers, linear solvers, et cetera, kind of things we're learning about here today. Differential algebraic equations almost always require implicit methods. That non-time evolution, just a constraint equation, makes things stiff in general. Now, multi-rate methods are ones that where you're going to take some parts with big steps and some parts with little steps. Those can be preferable if the thing that you want, an accurate step for the slow operator could be really big, but that slow operator is so expensive to calculate, you don't want to calculate it as frequently as the fast operator. So again, that kind of rules of thumb to think about. Okay, so we don't just want to take time steps that we know nothing about. What we really want to do is we want to solve your problem. And so if you know something about how accurate your data is or how accurate the solution you need to obtain is, we want to take the time steps that match that accuracy requirement. Okay? And so that's what time adaptivity is all about. So again, stability alone shouldn't dictate the time step size you use. You want to make sure you take time steps that are accurate and stable. Okay? And so if you have some maximum stable step size, say this big, but the solution you get with that step size is inaccurate, what step size should you take to get a solution that is the accuracy you need for your engineering application, whatever, and get that as quickly as possible? So at each internal step, adaptive methods will compute both a solution and an estimate of how much error was introduced in taking that step. It then looks at that error, that's error estimate for that step, it's called local truncation error, and decides if that local truncation error is small enough to be acceptable or if it was too big. And if it's too big, it just throws away everything it just did, makes the time step size smaller, and recomputes the step. Okay? But it wouldn't let you take a really terrible step and keep on going, because you can't recover from a terrible amount of error in one of these time marching steps. We have a number of advanced error controllers that try to adapt these step sizes to meet all kinds of objectives. So we don't want to have too many failed steps. Those are just wasted computation. We want to take the biggest step sizes as possible because that gets us to the end faster than you'd get if you take little tiny ones. But we also like smooth transitions in the step sizes. So if you take big, tiny, big, tiny, big, tiny, it's been shown that you can, that can induce additional error into your calculations as opposed to taking things that are kind of a smooth transition of step sizes as you go. So as we'll see in our hands-on exercises, and as we've seen in a lot of other applications we've worked with before, adding in time adaptivity can really lead to much more efficient calculations than you'd get with a fixed time step size method alone. And that's especially true if you have a problem that the dynamical timescale changes as you integrate. Maybe at the beginning it needs to take small time steps to be accurate, and later it can take gigantic time steps. If you just tell it take a time step size of 1 millisecond, you're going to have to take the small ones everywhere, whereas an adaptive one might track that dynamics appropriately. Okay, so I mentioned I'm going to talk a little bit about sundials, and then the next slide I'm going to talk about PETSC and Trilinos. So in sundials, it stands for the suite of nonlinear and differential algebraic equation solvers. And as the name kind of implies, we have a number of different methods for solving different types of ODE initial value problems. So the workhorse that everybody kind of knows is called CVODE, and it solves kind of standard initial value problems, where you include all of the physics that you're going to solve for in the right-hand side function f. RCode is the one that's the newest member of sundials. And this one allows you to split the right-hand side into multiple components. Those can be IMEX splittings. They can be multi-rate splittings. You can have multi-rate plus IMEX and have like a bunch of different layers of F1 through Fm. But it allows you to really think about partitioning the problem in some physically relevant way. on the left, we can have a time-dependent mass matrix for finite element type calculations. Multi-rate, which is also our code, now we're thinking about fast and slow. It doesn't allow the M yet. We haven't decided if we want to support the M there or not. And then there's IDA, which is the DAE solver. And so there we saw this kind of problem before. If you have an incompressible, say, Navier-Stokes, and you have this algebraic constraint equation, how do you incorporate that? And by solving these problems, we really mean that we're going to adapt the time steps to really match a desired error. And so if you, error here is our estimate of the error, this local truncation error that I mentioned a moment ago. And if you supply two things, a relative tolerance, it's a scalar, and if you want, say, 5 digits of accuracy, you give 10 to the minus 5 for RTOL. If you want 2 digits of accuracy, you give 10 to the minus 2. And so it's a scalar value that kind of says how many significant digits would you like in the solution. ATOL is an absolute tolerance, and so this is like a floor. Anything that's at ATOL is considered noise, and so typically ATOL is lower than RTOL. But if you have what's nice is that when you're solving a problem and you're using physical units like meters and centimeters and grams, whatever, some of your solution components could naturally be 10 to the 50, and other components could be 10 to the minus 20, and those are encoded in this ATOL. It tells you what's a noise level for each component of your solution. Well, once you've declared your tolerances and we've estimated our error, we make sure that every step we take doesn't violate this constraint. Okay? And so if it does, then we're going to throw that solution away and recompute again with a smaller step size. Okay? All right. So other DOE type time integration packages, ATPESC has a TS module, and they provide a unified interface for implicit, explicit, and IMEX, ODEs, and DAEs. All of their problems, they focus on this general form. F is going to contain everything that's stiff. G is going to contain everything that's non-stiff. And so they can do IMEX or explicit or implicit, et cetera, by thinking of this generic problem definition form. Trilinos, there's an older thing called Rhythmos, but that hasn't really been developed in recent years. But their newer one is called Tempus, and it looks a lot like our code. And so basically, they support the same types of problems that our code does. They have another form that they support, which is for Newmark integrators for second-order ODEs. But in general, they support the same kind of IMEX type splittings. They don't have multi-rate, but they have IMEX. All of these, SUNDIALS, ATPESC, Trilinos, they do time adaptivity. So they're going to try to track the time step sizes to match the application, your needs, based on your tolerance values you've specified. And they all have a range of algebraic solvers. So if you have an implicit method or an IMEX method and you need to solve algebraic things, you don't have to code up every piece of the nonlinear solver yourself. You can rely on other utilities for that. Okay, so when you have an implicit method and you need to solve some nonlinear algebraic system, however you write it, you can always take your implicit method and rewrite it as a root finding problem. And you need to find an x such that f of x equals 0. So ATPESC is doing their session right now in the other room on this exact problem. The whole session's just on that and the composable types of nonlinear solvers you can put together to do that. And I'll defer to if you want to download Richard's slides to look and see the kinds of things they offer there. That would be a great idea. In general, nonlinear solvers have to be iterative. There's very few nonlinear equations where we have analytical solutions to them, and we don't really code those up in software because we don't know that you're going to have exactly this type of nonlinear problem. So what types of nonlinear solvers are out there? And they typically reside in two families. There's going to be fixed point type methods and Newton type methods. And so the idea behind a fixed point type of a solver is they really only need f. So if you've coded up this f, or if you've coded up your little f and then the time integrator has turned that into a big F, which SUNDIALS will do, then they're going to evaluate f in different ways to try to converge to a solution to this root finding problem. They don't necessarily converge very rapidly. They'll have a linear rate of convergence. They're pretty robust usually, in that the domain of convergence can be wider than maybe with some Newton methods. And so, but they're relatively slow, but cheap. Each iteration is really cheap to do. Okay. Newton-based methods need both this f and the derivative of f with respect to its inputs. So if f is a vector valued problem, as most everybody's going to be doing here at ATPESC, then an x is a vector valued thing. This is a matrix of all the partial derivatives of each component of f with respect to each component of x. Okay, be it dense, be it sparse, be it matrix vector product type thing, and so you can go see the algebraic solver type things or the direct solvers and all those kinds of stuff that we've had these other sessions on. Newton's method requires that you have these things and you can solve linear systems with this J. And so you can see all the various linear solvers talks that we have today. Newton methods typically converge quadratically. Sometimes they'll only converge superlinearly, which is still darn fast. But that lower rate of convergence is typically based on how well you made maybe approximations, so you're not actually getting the true Jacobian, you're doing some approximation to it, or maybe you're not solving the linear system super well. For most problems, Newton is going to be algorithmically scalable. So if you want to scale up to the biggest supercomputers out there, that's okay. Newton's method on its own is usually just fine with that. If it takes 4 Newton iterations at small scales, it probably still takes 4 Newton iterations at really gigantic scales for most PDE type applications. The kicker there is, of course, solving the linear systems and finding a scalable linear solver for that piece inside the Newton method. Okay, so I'm imagining a bunch of folks today are going to talk about why using solver libraries, and probably in our panel, people are going to talk about this as well, but I'll have a little soapbox for the moment. So many applications in the physical sciences and engineering biological sciences, when they have a time-dependent problem, the very first thing that they'll do is they'll say, all right, you grad student, I want you to code up forward Euler, and I want to see results, and I want to look at the pictures, right? And you'll say, well, okay, fine, and you do it. And you can code up the simple things. You might not know what step size to use. You might not be doing high order. You might not be doing other kinds of fancy pieces. But you can get started really quickly. So why go to a library instead of just continuing on that path of recoding everything yourself? So solver libraries really allow this time adaptivity. And so that's a harder thing for you to tell a grad student to do. Not that you can't do it. All of you are capable of doing that if you look it up. But do you want to own every piece of everything, or do you want to let the experts who have built something kind of provide these tools for you? They often have seamless integration with scalable algebraic solver libraries. And so in SUNDIALS, we can hook directly up to ATPESC or Trilinos or Hyper to do these scalable linear solvers all day long. ATPESC, of course, has them built in. Trilinos has them built in as well. They have native support for cutting-edge GPU hardware. And so instead of having you take your Fortran code that your advisor wrote and now you have to add in OpenACC or something to it, as long as you're using things appropriately, then we'll be able to hook to these backends to really leverage GPU resources. And one of the biggest things is that we'll have options for later use that you don't use that first iteration, but maybe you need to do event handling, so finding some weird thing that happens and hone in on that we call that temporal root finding. Sensitivity analysis, you have constraints on your solution. Adding those kinds of things is harder when you're just kind of hand coding everything yourself. But these are options that are parts of a lot of our libraries. So for more information, you can click on any of these to get access to each of these solver libraries and kind of see what's in them. So David's going to start into some hands-on lessons. And so I hope that all of you maybe have already logged into Theta GPU, or if you haven't yet, then you do now, and you request that node. And basically, he's going to cover 2 things together with you on explicit time integration and implicit NIMAX time integration, both fixed time steps and adaptive time steps, et cetera. And then kind of an evening hands-on, a homework hands-on, whatever you'd like to call it, is going to be one that looks at preconditioning. And so that one's not necessarily going to be interactive. But if you do that and you have questions, you can always let us know. Okay? So with that, I'm going to give David the floor.
Okay, so hopefully you guys have already done kind of the first section here where you've gotten onto Theta. You've already copied over the hands-on folders into your home directory. And you guys have hopefully in some previous sessions gotten on Theta GPU and run some things. So we're going to switch over here specific to the time integration tab. Reverse scrolling. Sorry. All right. So I'm going to go into my track 5. Into my time integration sundials and into my Theta GPU directory. And for me, I've got this little runner here. Okay. All right, so I'm in now my home directory where we've got all these example programs. Right, so here I am. We've got an extra module. I'm not on Theta GPU yet. Okay, let me first get on Theta GPU, and then we can actually load modules that are on Theta GPU. So while that's coming up, let's kind of scroll through here. Well, what we're going to do is we're going to load this extra conda module because we've got a Python script that parses some output files so that we can look at some data that comes out of the time integrator. All the hands-on, so there's this other directory, there's this SUNDIALS plus AMRX directory, so that's got all the source code for all the hands-on that we'll be going through today. So if you want to get in there, modify the problem, try out some different things that we don't go into through this hands-on session, you can do that. There's a build script in there to help you kind of get things going so that you can modify and play around with it. And I'll also note that all these codes are also up on GitHub. There's a link to it here, so if you want to clone this later or fork it and play around with it, you're free to do that. All right, so the problem we're going to be looking at is this advection diffusion problem. So you can think of this as we're taking some sort of contaminant and dropping it into a fluid, and then we're going to track that fluid flow in a 2D domain to see where that contaminant goes and then what its concentration is. So if that was like some sort of, I don't know, pollutant in the water, you want to know when the water is finally safe to drink. And so this can be modeled as a scalar advection diffusion problem, which we've got up here, right? So we're looking at the time rate of change of the concentration, how it's moving with the flow, and then how it's diffusing over time. We're going to look at this in just the square domain from -1 to 1, and it's going to start out at some starting state, and then we're going to evolve it forward in time, to some time 10,000, right? So how we're going to set this up is if you guys were in the AMRX spatial discretization session this morning, you guys heard a little bit about block structured AMR and that block structured library. So we're going to use that library here to implement a second order finite volume discretization in a space. And we're going to kind of sort of leverage all of the infrastructure that AMRX provides, and then we're going to have SUNDIALS hook into that to then do the time stepping for that problem forward in time. Specifically, we're going to use the RCode package out of SUNDIALS, which does explicit, implicit, and IMEX Runge-Kutta schemes, right? So we're going to start out with this initial Gaussian blob. We're going to drop it into a field where there's this particular flow and these diffusion constants. And so you're just going to see it kind of travel over to up and to the right, and it's going to evect along and also diffuse out. And we're going to look at 3 setups of this problem, as Dan had mentioned. We're going to look at this first hands-on, which is going to do explicit in time, and then we're going to look at implicit and IMEX later with parts 2. So there's 3 different executables. There's 1 and 2 for hands-on right now, and then later in the evening, if you want to get into hands-on 3, there's an executable for that also. All of these executables have various command line options, so you can change various parameters, which we're going to use kind of throughout this hands-on, changing the time step size, changing the method order, those sorts of things. If you want to find out what all of the options are, you can just run the program with this help equals 1, and it'll dump out all the options that you can run the program with. All right, so hands-on lesson number 1. So this is where we're going to advance this explicitly in time. So this is kind of maybe the first thing you might try. So it's a simple thing usually to code up and to get things going because you don't need any sort of solvers that you have to hook in. And so how do we work with the library to set up our time integration problem? Well, from the SUNDIALS point of view, we need to know essentially 2 things. We need to know how to operate on your data and then how to compute the right-hand side function. Right? And so how we operate on your data, well, we need to know how to do basic vector operations. Add 2 vectors, take a dot product, compute a norm, things like that. And so the way that's done in SUNDIALS is there's this nVector class, which is just like an abstract base class in C++, but we've done it in C. And so that can just be a wrapper to whatever data structure you have, and we say, here's 2 vectors, please add them together and hand us back the answer. And so what's nice about the AMRX SUNDIALS setup is that AMRX already provides a wrapper, a nVector wrapper for these multi-fab data structures that AMRX uses in their library. And if you want to kind of get into the code and see what that looks like and how you make these wrappers, there's some links here into the AMRX repo where you can see how you might set up one of these nVector wrappers. All right. So the second thing we need is how to compute your right-hand side function. And so if we move everything over to the over to the right here, you'll have your advection operator, your diffusion operator, and then SUNDIALS wants a function to compute this right-hand side. It's got this specific signature where we need to know the current time, where we're going to hand you the current time. We're going to hand you the current solution. we would like you to fill in the right-hand side vector, so what is the time derivative, and then we'll also hand you this void star pointer, and so we call this the user data pointer. This can be whatever you want. So if you've got some structure where you need to hold on to specific constants or values for your problem, like let's say the mesh size or the advection speed or the diffusion rate, you can stuff all those values into this pointer and then pull them out when you need them in the right-hand side computation. All right, and one thing that's nice about working in the AMRX library is that we can leverage this AMRX parallel for loop. And so what's nice is that this code, you can run it just depending on how you build it. You can run it on the CPU, you can run it on the GPU, you can run it on one node or on multi-node without having to change the code itself. You just have to build it, with CUDA turned on or off, or MPI turned on or off, right? And so what's nice is that you get all that capability from AMRX, and then SUNDIALS gets to inherit that from its wrappers, right? And so this library just builds on top of the other one to use to have performance portability. Right. So once we've got those two things, what's kind of the general structure of how we get stuff set up? Well, you've got to create an n vector that wraps your starting state, so your u0. There's a link here into the code where we just take an AMRX multifab, we fill it with data, and then we just put a wrapper around it. So there's a nice link here. And then once you've got your starting state, you can do a create call to the SUNDIALS library where you're going to hand us that starting state and then your right-hand side function and the starting time, right? And so that tells us how we're going to get started and then what function we're using to define the problem. So once we've got those two pieces, then there's an evolve function that you can then call that'll take you from some time, t0 to some time t1. And you just call that as you want to get from one output time to the next. You can call that in two modes. You can take a single step. We'll say, okay, take one step and come back to me. Or you can say, take as many steps as you want internally to get to that output time that I've asked for. Okay, so that's kind of an overview of the setup and the hands-on. Okay, now let's run the demo. Okay, in here, load conda, activate conda. Okay, so we've already talked about the problem that we're looking at, so I'm going to skip that message. So we're going to look at first in this hands-on lesson one, we're first going to look at stability, right? So let's say we're going to run this problem with a standard. So what we're going to run this with, just to avoid the error you get without doing MPI run, we're just going to have this at the front. We're going to run hands-on one. We're running the CUDA version of it, and we're handing it this input deck 1. And this input deck 1 just specifies various things like the time step size, the advection speed, and stuff like that. So in this case, we're going to just run it with a fixed time step of 5 and see what happens. Right? So AMRX is setting up, we're getting running, dumps out the input problems that it's set up with. That ran pretty fast, so about 2.5 seconds. We've run to our time of 10,000, but we don't really have an idea of what our solution quality is, right? We just set a fixed time step size and hope it's good enough, right? So there's this fcompare function that you can use to then diff the solution that it dumped out with a reference solution that I've created earlier. Right? So this fcompare is going to go and run over this, take the difference, and tells us that we're seeing, ignore these errors that come out. Fcompare is also used for CI testing of the library. So if it sees an error that's bigger than 0, it's going to tell us it's wrong. So ignore that. So here we're seeing the absolute errors are about 10 to the minus 8, and similarly here for the relative error. So we've got a pretty highly accurate solution. Now whether that's the accuracy you want or not, that's going to depend on your use case. But you're probably going to have to now go back and kind of play around with the time step size and see what time step size is going to give you the solution quality that you want, right? So we could say, okay, 5, or this is too accurate and maybe it's not that slow, but maybe it's too slow for us. So let's try making the time step size bigger. Let's try a time step size of time step size of 100. So here we can just specify this on the command line, and this will override the value that's in the input file. So run it here with time step size of 100. That was a lot faster. We were, what, 2.5 seconds here before. Now we're down here somewhere around 1/10 of a second. But the question is, what does our solution look like now? So we'll compare the output we just got to the reference solution, and well, it looks like we pretty much have garbage, right? We've got some, 3 to the 284th power. We just pretty much just call that nan. So not so great. So question to you guys, what do you think's happened? Why do we end up with a garbage solution in this particular case? Yeah, why did it blow up though? Yeah, it blew up.
Moving too fast, maybe faster than like sound speed or something.
Yes, right. So the time step size is probably bigger than our stability limit, right? So the flow speed is going to set some sort of limit, as well as the as well as the rate of diffusion, and we've got to respect those stability limits. And so here we're definitely going way too big, and the solution is just blowing up. All right. So maybe you guys can try running this a couple times. Maybe see what you can find, kind of just manually what that maximum time step size is. What could you what do you think the biggest time step size we can take here is without the solution going to garbage? So maybe just try typing in some values, trying in some different DTs, seeing what you get, right? So go back here, maybe change this DT 100, try, 50, 75, 30, see what happens.
So bigger than 5.
Yes, 5 is what we tried the first time, and that was an error of like 10 to the minus 8. So 5 seemed sufficiently small. How big can we get away with, though?
It's like between 21 and a half and 22.
Yeah, that sounds right. So if we run at about 21, still pretty quick. Error, 10 to the minus 6 seems reasonable. If we try 22, still runs pretty quick. But what does our solution look like now? Yeah, we're getting relative errors of, order 1. So yeah, so somewhere between 21 and 22, somewhere in there is where that stability limit is. And so that wasn't too hard to find here, but maybe in another problem that you're going to set up some shell script to go through and run through and try a bunch of time step sizes and try to hone in on what the right one is. But instead, we can maybe do better than that. We can use the error estimators that come with adaptive schemes and just let it pick the time step sizes based on a tolerance that we want. So how we do that in this setup for the hands-on is we just set the fixed time step size to 0. And so when it sees that we've said the time step size is 0, it's going to then pick the time step sizes for us. So we'll go ahead and let that run. Also pretty quick. Again, less than a second, not as fast as the solution that blew up, but supposedly this one should be accurate. So if we do the diff here, yeah, we're seeing solutions of 10 to the minus 6. And if you kind of saw it scroll by here, we're asking for an RTOL of 1e to the minus 4 and an ATOL of 1e to the minus 9. And so this is definitely better than we even had asked for. So we're doing a bit of oversolving, but again, we're not having to manually try to find out what the right time step size is for our problem. So we can also kind of look at some statistics. So there's this process arc step diags Python script that'll take this output file that got dumped out by the hands-on and process some statistics that come out of that and make some plots. So here we can see that over here, right, we had the smallest time step we took was somewhere kind of 1e to the, or 10 to the minus 3. However, we had some peak time step of 33 with an average of about 21, 22, right? So we're seeing that it is varying the time step as we go along. And then you can actually make a plot. There's a plot that's dumped out of this. The X forwarding on Theta GPU doesn't seem to cooperate, so I'm just going to put them into the web page right here. We can see the time step history when we did this run. That it starts out with a very small, very conservative time step to get started, but then it takes those error estimates and sees that it can really ramp up the time step pretty quickly, almost right away, up to things that are kind of, here's 10, so it's hovering right around that stability limit of, 20 something. Every so often it'll try to push higher and see if it can, and then we'll see that there's a failed step and it pulls it back down, right? So automatically it's kind of found this CFL and just hangs out there for this problem. All right, so maybe you guys want to try this out, maybe try some different tolerances, see how well they perform, see how close they get to, over-solving the problem, under-solving the problem, see what comes out. Try some different RTOL values. Yeah?
So does it know what the CFL comes from because you use
used a wrapper that said that it was a diffusion convection problem, or is it just dynamically figuring it out?
Yes.
Basically.
Yes, just based on the error that it's seeing. Yeah.
So is this adaptivity, in a normal hydro or something, maybe we'll use the time step is set by the sound speed or the maximum wave speed.
Yeah.
With the CFL, is this in addition to that or in place of that?
In this case, it is in place of that. There is also an option where you can hook in a function that tells us what the CFL is, and then you can sort of feed that back, and it'll look at the accuracy-based time step and the CFL-based time step, and then pick based on what's going to give you the best solution. Yeah.
So when it comes to like a reaction, diffusion, convection process,
Yeah.
it's going to be very stiff, right? So would sundials like basically carry out more tests to hone in on the right time step, or is there some sort of sub-stepping also possible?
So in this case that we're looking at right now, it's going to pick the time step based on the requirement of the fastest time scale. We're going to look at IMEX in a second. That's one way of sort of separating out. You've got an explicit part that's probably not as stiff and not as restrictive on the time step size, and then you have an implicit part that's probably going to be your stiffer, faster dynamics, and then that'll kind of, we'll look at that case for this problem. When you get into an advection diffusion reaction problem, then you're kind of getting into where multi-rate methods are really targeting where you've got a super fast time scale that then possibly needs to be subcycled.
So, but if I were to use the normal CBOD, like the explicit,
Yeah.
the time step would be chosen based on the stiffest chemicals, which
Yes.
is the smallest number.
Yeah. Exactly. All right. So just some stuff you could have tried. Try out 10 to the minus 2, see what happens. It's going to be faster, going to take fewer steps, but then the question is it, how accurate is it? Well, it's going to be, of course, less accurate, but it's not too bad. We're looking at, again, pretty close to our tolerances. We've probably oversolved less in this case than in the previous run. We can look at the sort of stats and see what happens, right? We've got smaller oversolve, roughly bigger time steps at some point because we're asking for less accuracy than we were before. So similarly, do a tighter tolerance, you're going to see it's going to do more work, more right-hand side evals. And then generally, error that's on the order of what we're looking for, but a little bit oversolved. And then we can look at stats again. It's taking, on average, a smaller time step size here. All right. So here we were running, I didn't say it, but we were running with the default fourth order scheme, right? And so maybe that's the right fit for this problem. Maybe we want a higher order scheme or a lower order scheme, depending on what the best fit is for our problem. So here we're just going to try out the eighth order method. So here we're going to, again, use this input 1. We're going to use variable time stepping or a adaptive time stepping. And here we're going to say what the method order is. So here we're going to set it to 8, and it's going to use the default 8th order scheme that comes out of the library. Again, runs pretty fast, not as fast as we saw earlier. It's, again, about a second. You notice that it's taking far fewer, if you looked at the right-hand side evals that came up earlier and the number of time steps, this is taking fewer steps than we did earlier. I think we took on the order of 240 something. I think I've got it. I think it's in here. Yeah, like 462, right? So we took about 462 steps before with the fourth order scheme. Now we're taking 260, but we saw that it took longer, right? We were sub 1 second. We were kind of 0.7 seconds earlier, and now we're a little over 1 second. So while we're taking fewer time steps, those time steps now cost more. It's a higher order scheme. It's going to need more evaluations of the right-hand side function in order to take that time step, but it also may give us a more accurate answer. So depending on what our tolerances are, a higher order method might be beneficial, or a lower order method might be beneficial if you need less accuracy. So something you guys can maybe try out, maybe play around with. Look at what the error is. Again, it's on a little bit oversolved, 10 to the minus 6, so more but still, it's still meeting the accuracy tolerances that we were asking for. So maybe something you guys can try out. Maybe try out some different orders, see what sort of solutions you get, see how they compare in terms of meeting the accuracy that you asked for. Yeah.
What do you mean by oversolve?
Oversolve. So here, right, the error is, some on the order of 10 to the minus 6. The relative tolerance that we asked for was 10 to the minus 4. Right, so it's given us more accuracy than we needed. So it's oversolved the problem. Right. There are things we could try to do to maybe make it more efficient. There's other parameters that we can go in and play around with and try to tune it for this specific problem. But out of the box, it's doing a little more work than we needed to. All right. Yeah. So something you could try out. You could try running it order 2. See what happens. Right. Second order method, we're taking a lot more time steps than we did previously. Right. So it's lower order. It's less accurate. It's has a smaller stability region, so it's going to have to take smaller time steps, do more work, right? But it's still going to give us a usable answer here, right? We're a little bit undersolved here, right? We're at 10 to the minus 3, right? But still, pretty good. Try 5th order here, see what it does. Right, again, taking fewer time steps this time, right? Because it's higher order, more accurate, more able to take larger time step sizes, but they cost more, right? This is here what we were 10, we're 0.7 seconds. Up here we were 0.9 seconds. So it's actually faster for this one to go higher order than the second order method, right? And again, it's giving a similar error, right? 10 to the minus 3. All right, so that was explicit. We saw that we had, time step size limits, and maybe that's okay for our problem, or maybe these time scales are things that we want to step over because they're not really of interest to us, right? So let's look at doing a implicit method. So this is going to be hands-on 2. So we're going to have the same sort of setup, and let me switch back over here for a second. So if you open up the not the executable, but if you open up the source code for hands-on 2, you'll see a couple places that are marked, updated from hands-on 1. Right, so there's some very small changes to go from explicit method to implicit method when using this level library. Really, it's when you set up, you say, well, I'm going to hand you an implicit right-hand side function rather than an explicit right-hand side function. And now I need to hand you a solver object to do the solve, right? So that's all that you really need to do is you need to say, I'm going to do an implicit problem, and here's a solver to run with. So pretty minimal changes when you're using a library to just switch between the explicit and the implicit version. So let's go back and try to run this hands-on 2 with the input deck. So this is doing the same thing we did first off in the explicit case, where we're going to run with a fixed time step 5, the same set of parameter values. And you might notice it's taking quite a bit longer. It's doing a lot more work. So any idea why we're doing so much more work?
Implicit aspects.
Yeah, right. So we've got to do an implicit solve now. So we're going to have a lot more work that we've got to do per stage, right? So you can think this is what, 4th order method. So it's probably got 4 implicit stages. So that's 4 solves we're doing every time step. So there's a lot more work. So it took, about 25 seconds, where we were, maybe on the order of, I think we were 2.5 seconds when we did this with the explicit case. But again, here we're getting a quality solution here. Again, much smaller than we asked for. So let's try that 100 time step again, right? So this is what blew up when we did the explicit method. So let's try out this time step of 100 here and see what that happens in the implicit case. So again, a little bit slower. We took 5.7 seconds. But the question is, what does our solution look like in this go around? Well, now we've got a reasonable answer, right? We're seeing errors kind of on 10 to the minus 4, so right around the error that we had asked for, right? So the question is, why does it work in this case when it didn't work previously? So why are we able to take a time step of a 100 here and get a reasonable answer, and we weren't previously?
Since it's using our emails, it's an implicit solver, so we can take a higher time step?
Yep, exactly, yeah. So here we're using an astable scheme, so we're no longer bound by that stability limit. So here we're just worried about, is the solution, is the time step that I'm going to take accurate, right? I don't need to worry about that stability condition also. So maybe you guys want to try to run this. Yeah?
I just have a question. So this is a linear problem, right?
Yes.
So it says it's using Newton iteration.
Yes, so it's generally set up to assume that the problem is non-linearly implicit, but you can set a flag to tell it that it is a linearly implicit problem, and then they'll take 1 Newton and then do however many linear solves that it needs.
And if it's really non-linear, does it, like, I mean, does it use like a finite difference approximation of the code?
It depends on what the linear solver is. So here, because we're doing this parallel PDE case, it's going to do a Newton-Krylov scheme, and so it's going to use a Krylov solver for the linear solver specifically. It's using GMRes, and it is doing a finite difference, a approximation of the Jacobian vector product. So it's not actually forming the in this case would be banded system. It's just approximating that with a directional derivative. Yeah. But if you were doing, let's say, like just a reaction system on a single node, then you could have it build through finite differences or through a user supplied function, the actual Jacobian itself, and then depending on your use case, one of those might be better than the other. Generally, for the PDE cases, people are going to use these Krylov solvers. For things like reactions, they'll generally use kind of dense direct solvers. Yeah. All right. So did anyone try out some other time step sizes to see if they could, make the solver croak? Try to push it as high as you can. How high did someone go? How big? 500? Yeah. 500 I think still works. It just takes a while. If you looked at like the number of linear solves that it took, it gets to be pretty ridiculous. Like I think it starts taking 60 linear iterations per nonlinear at that point. So you're doing a whole lot of work. I don't remember what this one was, but it's taking, it's only taking, 340 nonlinear iterations, but it's taking more than 10,000 linear iterations. So it's doing a lot of work each step. Did anyone, let's see. But is it still a reasonable solution? Yeah, we've still got a reasonable solution, even with a time step of 300. So 500, I think, is still a good solution. Did anyone try bigger? Did anyone try to push it higher than that? 1,000, yeah, that's a good choice. That's what I tried, just to see if it would blow up. Yes, and it doesn't blow up so much that the solver it's just too much work at a time step size that big. You could probably let your solver do more iterations maybe, and it would maybe be able to solve it, but at this point it's just giving up. All right. So that was all with fixed time step sizes. So we can do this same thing we did in the explicit case. We can let it run with an adaptive time step size. So setting that fixed ET input to 0. Let it run through. So now we're down to about 3.5 seconds, so a lot faster here in the variable time step case. See what our solution looks like. Yeah, so right on what we were asking for, around 10 to the minus 4, right? So we're getting a nice solution there pretty quickly, and it's something that we know is going to be stable, right? So what is this? Yeah. Oh yeah, so what does our average time step size look like? So if you remember, which you probably don't from those stats that flew by earlier, the explicit method had an average time step size of around 22. Right? It started out small and ramped up and kind of hung out at around 21, 22. So here we can see that on average with the implicit method, we've got an average time step size of about 75. Right? So it's able to even push even higher. So if we go over here to our web page, take a look at the implicit case, it's similarly starting out at a really small time step, pushing that time step up pretty quickly, and it just keeps pushing it up higher and higher and higher as we go on. Right? It's up here, getting over 100. Right? As we've gone out towards the end. So the question is, Why are we able to just keep getting bigger and bigger time steps with this problem? Right. We're just keep ramping it up. Is there any reason why that's happening? Maybe think about what's physically going on with this problem.
Coming closer to your final solution.
Yes. Well, yeah, I think you guys are both right in that this is going to essentially start diffusing towards some sort of pretty much steady state. Yeah, like the problem is going to diffuse out and it's going to become more homogeneous, and it's going to essentially get easier and easier as time goes on. And the integrator's tracking that. Seeing the problem's getting easier, I can keep pushing the time step size up and up and up. And it keeps doing that throughout the rest of the problem. All right. So if you guys want to try that out, maybe run it a few more times with a couple different RTOLs, see how it performs, see how it changes. You guys can try that out. I think in the interest of time, I'll just keep moving forward. Yeah, so I'm going to try it here. RTOL 10 to the minus 2. So low tolerance, see what happens. Runs pretty quickly. Gives us right on the error that we asked for, around 10 to the minus 2. Looks perfectly good. Try a higher tolerance, 10 to the minus 6. See what happens there. Takes a little longer, does a little more work, but we're asking for a better solution here. But still, a little over 7 seconds. What do we have for error? 1 times 10 to the minus 6. So a little bit undersolved, but yeah, no, right on, right? Because we asked for 10 to the minus 6 in this case, right? So it's hitting the accuracy that we asked for. All right, so that's fully implicit. So here we've got an advection diffusion problem. You'll often see diffusion treated implicitly, generally because you can think that its time step is kind of proportional to the discretization mesh size squared, whereas advection is only proportional to the mesh size itself, right? So the diffusion is going to have a stricter time step size limit, generally speaking, than our advection, right? So we could think about splitting these up, doing the diffusion implicitly, doing the advection explicitly, right? So that's this hands-on 2 still, and we're adding this RHS ADV, so the advective right-hand side. If we set that to 1, it's going to switch the advection right-hand side from being implicit to being explicit, and now we're going to use an IMEX scheme. Right, so we're going to go ahead and run this again with a fixed time step size. Again, you've still got that implicit solve, so we're still going to have a higher cost. So it's still going to take some time longer to run because each step now costs more. But we do have some stability benefits. And if this does like it's done all day, yeah, so that ran about a little under 20 seconds. Took. And is the tight accuracy that we saw in the explicit case. So did you guys notice? You may or may not remember kind of what the fully implicit ran at, right? That was about 25 seconds, right? So here we are seeing some benefit from splitting this up and having a explicit advection term and an implicit diffusion term, right? We're about roughly 5 seconds faster here. If we scroll back up and look at the output, right, we've got these explicit right-hand side evals and these implicit right-hand side evals. So how many times do we call the explicit right-hand side? How many times do we call the implicit right-hand side? Does anyone have a thought of why these are so different? Why is one so much bigger than the other?
The time step restriction from the implicit is larger, so you need smaller time step, more evals.
That is going to be part of it. Yes, we are going to be taking more time steps in this case, which we'll look at in a second, because you're all right. We now have an explicit term, which is going to give us some sort of stability limit, which is possibly going to make us take smaller time steps. The diffusion is going to dominate that, though, right? And so the implicit part is still going to get us over that. Is there something else that cost could be coming from? Yeah.
For the implicit function, you need to evaluate it to do the Karloff.
Yeah, that's right. This is still part of a solve, right? So the right? So the diffusion term is still showing up in that nonlinear solve and in that linear solve, and so every nonlinear iteration that function's called, and then to do that Krylov solve, it's called also, right? So it's getting called multiple times per time step, whereas this explicit right-hand side, it's getting called once each stage, so far fewer. So it's like getting called 4 times per time step, whereas this is getting called however many iterations that we have to do. And so that's one other thing. If this is really costly, it's nice that it's called less, right? If this is really costly, well, then we need to do some more work on our solver. All right. Yeah, so if you guys want to try out various fixed time step sizes here, and also you guys can kind of dig into that and see how that works. See if you can find that stability limit like we did previously. So if you guys want to run with, last time I don't remember what we got, 21, 22 was our limit, right? So did we gain anything in this IMEX splitting in terms of stability? So if you guys want to maybe try out, I don't know, 30, 40, 50, see how high you can push it up in this case. Maybe let me know what you find. All right, we did not go that far. All right. Anyone have any luck trying out some time step sizes? I'm going to try 53. See what happens. It's an odd number, so you're probably guessing I picked this one specifically. See that? Okay, still a reasonable solution at 53. So that's more than double what we had in the explicit case, right? We were limited to 21, 22 there, right? So now we're able to take a bigger time step size because that implicit portion is no longer pulling us back, right? So now that's an implicit part. And if we try a little bit bigger, if we try 55, see what happens there. Again, it ran pretty quickly. But always the question is our solution accurate? No. Now we're seeing that we're getting relative errors kind of around 1, right? So before, with the fully implicit scheme, we could just keep pushing this up and up and up, right? Because we had an A-stable scheme. But like one of you said earlier, we've now got an explicit portion here. So now there is going to be some sort of limit that we've got to, that's going to pull us back on the time step size. It's bigger than it was previously, though, so we can take bigger time steps than in the fully explicit case. All right. And this was still doing fixed time step sizes, so similarly, we can run this with variable time steps, adaptive time steps, let it run. Faster in this case, right? Much faster now that we're not stuck doing one time step size for the whole problem, right? We're running at about 4 seconds here. See what our accuracy looks like. Yeah, so we would 10 to the minus, so 2 times 10 to the minus 4. Yeah, so we're right around the tolerance that we'd asked for. All right, and see what the time step profile looks like in this case, right? So we started out again, really small time step, minimum time step, about the same as before. We are pushing up that time step size higher, right? We're getting up to around 120, and we're getting an average of about 54. So we're hovering, that average is hovering right around that CFL limit. All right, so if we go back up here to the website, look at the plot. Again, rocketing up from that starting time step size, getting up here to around the CFL. We're seeing more oscillations of the time step size in this case. It's really trying to push it up and coming down and push it up and coming down. So there are some things that we could try to maybe change the algorithm that's used to pick the time step sizes. There are lots of tuning parameters in there also, so there's some things that we could do to try to help this out, but still, it's doing a good job of finding that maximum time step size and going right to it and following it. All right. Okay, so that's kind of what I've got for the hands-on part of today. So we're going to go over here to the outbrief and kind of summarize what we've looked at. So we've looked at explicit schemes, implicit schemes and IMEX schemes, both with fixed time steps as well as adaptive time steps. And we've also played around with the order of these schemes. So there's lots of different things that you can pick from. But really, you need to look at your problem and say, what properties do I need? Right? Do I need an explicit scheme? Do I need to track the fastest parts of the problem? Do I need an implicit scheme because I'm CFL limited and I really should be able to take a larger time step size for the accuracy that I'm asking for? Do I need something that's higher order, lower order? Hopefully you've come to believe that using a adaptive time stepping is the way to go rather than trying to just plug in time steps and see what works and try to compute an error and see if it's good. Because you can think, here I've got a reference solution that I can compare to. But as the problem gets more complex and the physics gets harder, knowing how to to make a reference solution and then kind of home in on what the right time step size for your problem is going to be very challenging, especially as you add in more physics and do a multi-physics problem, you get multi-rate schemes. So having a way to set a tolerance level for the accuracy you want and follow it. Hopefully you guys kind of bought into that's the way to go. And hopefully you've also seen that it's pretty easy, at least here, and you guys can dig into the code itself, that once you've got the interfacing to a library set up, you get lots of knobs that you can tune and play with, try out various things, right? Here, if you dig into the hands-on file and look at hands-on 1 versus hands-on 2, there's, I don't know, 20 lines of code that change maybe at most to go from an explicit method to an implicit method, right? All you do is change one input and and then create and add a solver. So it's very little work, right? So using a library can give you a lot of benefits in that. So I'll very quickly talk about the hands-on that you guys can try out in the evening if you want. This is set up to run on Theta KNL, so on the KNL nodes of Theta rather than on the GPU nodes, because you guys can scale out to more nodes on Theta than we can on Theta GPU, right? We're all just getting one GPU for today, so it's kind of hard to scale things up. But there's some setup instructions here. It's very similar to what you guys have done for Theta GPU, just logging in, loading the right modules and stuff. And so what you'll try out here is, in the implicit problems, or in the implicit methods that we were doing before here, in the fully implicit and in the IMEX case, we were using GMRes, and we were using GMRes without a preconditioner, right? So as we scale this problem up and make it bigger, we're going to see that it's not a scalable solver. That we're going to generally have the linear iterations kind of keep going up as we make the problem bigger and bigger. And if you add on a preconditioner to help make that solver more efficient, hopefully you'll see that you'll get a scalable solution. So if you guys have gone to the Mulu talk earlier, or if you're coming to the Hyper talk later, you guys will hear more about scalable solvers. I think we've got a couple of minutes for questions if you guys have any more questions. I know several came up during the talk, but yeah.
For your multi-rate time steppers,
yes.
Do you support like more than 2 levels, or is it just
Yes, you can do it. Right now, you've got to roll a little bit of your own code to do it. But yes, you can nest one under the other. Yeah. Yeah. And that's something I'd like to make easier natively for users. So right now, two levels is easy. More than 2 requires a little bit more work, but not much. Yeah.
Do you support any L-stable models, or is that not something you go after?
We have L-stable schemes in here also, yeah. So there's a lot of tables. I think all of the default methods are most of them are L-stable. I'd have to look at the tables.
The Dirk ones are.
Yeah, the Dirk ones are? Okay, yeah. So all the Dirk ones are. Yeah, and if there's a particular method that you like, that you want to use, you can also hand it a lecture table, and it'll just use that. Yeah. So plugging in your own scheme or coming up with your own scheme and plugging it in is pretty straightforward. All right. Any other questions? Okay. Well, if not, we're at 2:44, so you guys have a break at 2:45, I believe. And then I think we're back at sessions, I think a half hour after that. All right? Thanks, everyone.